So last time we started our discussion on the interaction between atoms, representative of matter with light, so which is EM waves. It is a big topic by itself. You can find dozens of big books on this very important topic called light-matter interaction. No matter you are interested in particle physics, solid state, atomic, AMO, whatever, it has to do. It has something to do with this big topic, because if you put your particle, either it is an atom or even a smaller nuclei or elementary particle or molecules or solids, if you just put them there and not plopping it, you don't know anything about it. So in physics, we need to do something to the system and see how it responds. A very convenient way to plop a system is to use EM waves, or generally speaking, we will use the term light, although some of this light are not in the visible region. For example, we will use infrared in plopping some molecules vibration. Nonetheless, you don't prop anything, you don't know anything about it. So this big topic about using EM waves or light to interact with what you are interested in becomes a very convenient experimental method, as well as a very important theoretical topic. So let's get into the topic. First of all, let me remind you of some phenomena in this big topic. It is related to, for example, you can go to the library site and look up optical properties of atoms, of molecules, of solids. Again, you will find volumes of textbooks on the topic. Here on the bottom here, I try to depict, so you have atom, you have the Hamiltonian of hydrogen or helium, whatever. You can solve this time-independent Schrödinger equation so that you get all these energy levels. Each has its wave function. Sometimes it may be degenerate. Nonetheless, typically in the low-lying energy region, they are discrete energy levels. So let's say the atom initially is in the thick line, so lower in energy. It is in this particular state. So you start sending in light, incident light, to interact with the atom. And then maybe sometimes later, the atom is so-called excited into a higher energy final state. So the description of this thing becomes, it is a stimulated absorption. I include the word stimulated here to go parallel with something called stimulated emission. Of course, for absorption, if you don't stimulate it, there's nothing to absorb. So usually it's simply called absorption. Nonetheless, this word has meaning. At the outset, let me tell you what it means. It means the probability for this to happen, absorption to happen, is proportional to the strength of light coming in, or intensity of the light coming in. That is what the word stimulated means. The stronger the stimulation, the more ready this process will occur. Similarly, it so happens that there is a process called stimulated emission. It's very similar to what we just discussed. So initially, the atom is in some higher state. There is a incident light comes in, and then a bit later, the atom is found in a lower energy state. Instead of absorbing the light, it even gives out one more so-called photon of energy h bar omega. So this light seems to be stimulating emission from a higher level to a lower level and emit more light. Again, it is called stimulated because the probability for this to happen is again proportional to how strong the light that is interacting with the atom. We will work out the simple theory within our Schrödinger quantum mechanics to understand stimulated absorption and emission. There is something that looks very natural, but within Schrödinger quantum mechanics, it is more difficult to explain. This natural thing is spontaneous emission. The phenomena is as such. We have an excited atom to start with. We do nothing to it. That is to say, there's no incident light. We just leave it there. But then, actually, in a very short time, usually, the atom will be de-excited by itself. That is called spontaneous. In Chinese, it's called 自发的, 自发的. You don't need to do something to it. It will happen by itself. So this is spontaneous emission. I already said that it is more difficult to conceptually explain this phenomena within Schrödinger quantum mechanics. For the very reason that if you learn your quantum mechanics well, these are energy eigenstates. And if a system is in its energy eigenstate at time 0, it will stay in that state for time at time t and so on, because it is an energy eigenstate. Therefore, the fact that the excited atoms will come down to a lower energy state, to the ground state usually, by itself is a mystery within Schrödinger quantum mechanics. But first of all, spontaneous emission is a very important process. Many of our lighting devices basically rely on spontaneous emission. We just do something. We pay the electric bill to excite the atoms up there, and then it will come down, and then we get light to use. This is light emitting devices. Okay, so it works, it happens, but within Schrödinger quantum mechanics, it is something uncomfortable. Or is it? So if you read this carefully, I use quotation marks here saying we are doing nothing to the excited atom. Well, we put the atom, let's say we even pump out all the air in our apparatus. So it looks like we are putting an excited atom in vacuum. But even vacuum turns out to be something, it's not nothing. And that is the physics, the difficult physics behind explaining spontaneous emission. So the mystery here actually refers to, although we put an excited atom in vacuum, vacuum turns out to be EM waves ground state. So it has something in it, 0-point motion. And it is that vacuum, the ground state of EM wave, that is stimulated, is stimulating the atom to come down. So it is a very involved explanation, even harder than the very famous stimulated emission from which we get laser. So after we have this big picture of the phenomena, let's go into interaction. First of all, the big idea is that we have transitions between atomic states that is due to light atom interaction. So that is the big picture. Let me emphasize this point one more time. From this point backwards, you learn how to solve the Hamiltonian of the atom alone. For example, hydrogen, helium, even hydrogen with spin orbit interaction, it is atom alone. Well, we solve it happily. For example, hydrogen, we know that it is NLMLI alpha theta phi, separation of variable, very happy, okay? And then usually for central force atoms, the energy depends on N and L. For hydrogen, it only depends on N. So that's what we know. Let's say initially, at time, you can set whatever time, call it 0, so T equals 0, it is in an energy eigenstate. From Schrödinger quantum mechanics, we know that at a later time T, it evolves, but it evolves with its own phase factor. So given that this is an energy eigenstate with energy labeled by N and L, this is the corresponding phase factor. Okay? So now, we also know that this is the coefficient for which if we take the absolute square, it is the probability of finding the system to be in this state at time t. This is last semester's quantum mechanics, nothing fancy. However, if it is a phase factor only, the coefficient square is 1. Therefore, that is the statement that I was trying to make for the spontaneous emission mystery. So, if initially the system is in an energy eigenstate, at any later time t, it remains 100% certain in that energy eigenstate. Well, if you only know this part of quantum mechanics, which is good, there will be no transition. Atom in an eigenstate at time now, it will be at that same eigenstate forever. There will be no transition. But Schrödinger quantum mechanics works. We don't need to learn something new. When we have an incident light, the Hamiltonian becomes more complicated. There is light interacting with atom. We need to write down additional terms in the Hamiltonian to describe the whole physical situation. This is the first take-home message. Formally, the Hamiltonian becomes, we have the atom part, of course, then we have the light atom interaction part. So this will serve as our perturbation term. So we have additional term. Even more formally, within quantum field theory, we should even include a term that has to do with describing the EM wave quantized part, so-called photon Hamiltonian. We are not going to write it out formally because that is beyond the scope of our course. We need to quantize the EM field. Nonetheless, it is very easy to grab the big picture. Without anything, you solve this isolated atom, lonely atom. And then once we include light into our consideration, this is light alone without the atom. So to be fair, equal footing. And therefore, we also need to include how this atom, free atom, and free photon, how they interact. This is the interaction term. So all in all, once you include light, the Hamiltonian is not atom alone. Therefore, simply put, this state it is an eigenstate of H atom alone. That is before light comes in. But after light comes in later time t, this alone is not an eigenstate of the whole Hamiltonian. Therefore, it is bound to change. Schrödinger quantum mechanics, nothing fancy. Okay, good. So take home message, atom, the Hamiltonian has interaction term. And this interaction term is responsible for transitions to happen. So in a pictorial way, the two processes that we discussed can be now, qualitatively speaking, explained as follows. We must include light into the full description. Absorption, for example. Before absorption happens, the full specification should be atom in a lower state, and we have one photon, H bar omega. Now, that description has to do with the atom and the light, because our full Hamiltonian has all these ingredients. And then after absorption, it is in a state that we have to describe it as atom in the higher state, excited, and then the photon originally there now disappeared, no photon. This is the full description, atom and photon part. And why this could happen to the other side, okay? That is due to the interaction part. That is the concept, qualitative concept. So, take home message, the second one, it is the interaction term that leads to transitions, okay? And the description, to be fair, of a state should include both the atom description and the light part description. So the point is, we have to look into this interaction term. What is the mathematical form? If we can write it down, then we know the characteristic of this interaction, and therefore we know what theory to develop to explain its effects. Similarly, we can do the same thing for stimulated emission. I haven't write it out here. A stimulated emission at the beginning, atom in the upper state with one photon. Finally, atom in the lower state with two photons. Then that is stimulated emission. Or atom in the higher state with n photon. Afterwards, atom in the lower state with n plus one photons. Okay, so if you have this, then later on, if you are interested in, you want to learn quantum optics, you want to learn the formal quantizing the EM field, you will see how to write down this description mathematically. But you have to have the big picture first in order to learn the technical details later on if you prefer to learn them. Then how about spontaneous emission, the troublesome but simple thing? So I already hint at vacuum is not nothing, it is something. So roughly the picture is as follows. Before spontaneous emission occurs, the atoms is in the excited state, higher, and the light part has no photon, so nothing. And then afterwards, it is in the lower, the atom is in the lower state, and there's one photon. So that is the description of the atom plus light system. And then you may wonder, how possibly could this happen? You are doing nothing to it. But if you include light into the description, then again, using a little bit of your EM knowledge, I think you know this is the energy density in an EM field, right? Do you know that? Well, if you don't, you must have seen this in the capacitor, right? You have that, I hope. The capacitor energy density. And that is the inductance. There is an inductance, how much magnetic energy is stored in the inductor. Okay, so but if you had a EM waves trapped in difference, this is also the energy density in a EM wave. Well, if you look at this energy density is Hamiltonian density, right? Energy is Hamiltonian. So that looks like a Hamiltonian. And if you don't know English, it is even better. Do you see that it is very much like this? Right? Two quadratic terms. And therefore, it's not surprising to see that when you quantize EM fields, basically it is oscillator physics. And oscillator physics, the most important result is the energy levels, right? Evenly spaced h bar omega, and there's a 0-point energy. The 0-point energy is always there even for the ground state. Therefore, vacuum, as we see it, is ground state of EM field. And therefore, nothing is really something. Okay, so I will stop here because the formal thing here, you need to learn how to formally quantize a field. But if you have this big picture, then there is nothing mysterious anymore. So now, I would like to argue that what we are encountering is a typical time-dependent problem in quantum mechanics, and therefore, in the later section, we need to develop time-dependent perturbation theory. In addition, the question that we want to answer fall into the category of initial value problem. Initial value problem in physics means 初值條件嘅問題初始條件的問題. So you are given a condition at time, say, call it 0, and then ask what happened at later times. So this is initial value problem. And the Hamiltonian turns out to be time dependent. So let me motivate why we have this. The most important take-home message at the end is that what is the form of this atom-light interaction Hamiltonian, H prime, that serves as the perturbation. So let's start. Big picture first, technical things later. So we set a time called 0. You may call it T0 to be more general, seems to be. So before that, the atom is in some energy eigenstate that I call phi I. You may think the I as initial, okay? Or later on, we call it phi 1. Doesn't matter, you understand the situation. And then at some time called T equals 0, and afterwards, light comes in, there will be an atom-light interaction term kicks in our theory. In the Hamiltonian, or physically, the atom is there, light start to come in, boom, time 0, and continue, the light will continue on for some time t. And then we will look into the atom and ask, after some time t, what is the probability that it is no longer in the initial state, it becomes somewhere in somewhere called final state. So that is typically an initial value problem, right? And now let's consider what possibly the form of this interaction term will take. Of course, it has to do with matter atom light interaction. So we expect this term H prime to include both of these two systems variables. Namely, there must be something in this H prime that has to do with the electrons in the atom. And then there must be something in this H prime that has to do with the incident EM field. Only then it is describing atom light interaction. Logic, right? Simple. And then what we are going to do is that, roughly speaking, this has to do with EM waves. And EM waves, we know that we have electric field oscillating. So it must go like something like a vector amplitude and then cosine omega t, where omega is the incident light angular frequency. So that makes sense. When we have E field, rather naturally, it will interact with the electron's charge, right? And then we know from E and M again, an energy term can come out when this E field interacts with the electric dipole moment. Minus P dot E is an energy term, and we are going to use that to form our H prime. Here, we will focus on the most important light absorption or emission mechanism. This is called electric dipole mechanism. Very roughly speaking, you look up anything in your electromagnetic books, it will have that. So you have an atom, a nucleus, and an electron described by wave function. So it's like an electron cloud surrounding the nucleus. So EM wave comes in, it is the B field keeps on changing with time, right? Go up in this instant, shorter, 0, point down, and so on, okay? So this is EM waves. Therefore, the electron cloud will be shaped by this incident waves. And then, classically speaking, I'm using Griffin's E and M. So when the charge oscillates, it is accelerating all the time. Thereby, there will be some EM wave emitting. Okay, so that is the electric dipole mechanism. Quantum mechanically, we have to write down this part of the Hamiltonian. Again, the strategy is think classical, meaning think E and M, then turn things into operator. So that is the strategy. So let's continue. The idea is that I tried to draw a EM wave, a E field here, okay? So it is at a constant time, take a picture. So you have this wavelength over which the field is varying in space. So an important characteristic here is a wavelength. We know that light absorption, let's say sodium, yellow, right? So yellow, visible, once upon a time in high school, you know that it is 400 to 700 nanometer, right? So that is the wavelength in the visible region, typical of light absorption by atoms. The point is that the wavelength is much longer than the size of an atom. What is the size of an atom? So if you solve the hydrogen atom, there's only one length, the Bohr radius. Even bigger atom, more or less the same size. There's good Schrödinger reason for that. Think about it. So basically, we have the situation. The wavelength of the incident light is much longer than the size of an atom. Therefore, if we put these two pictures together, I mean this EM wavelength picture and the atom together, no matter you put the atom, the E field across the size of the atom is a constant. That is to say, across the size of an angstrom, the E field will not suddenly go from very, very high to very low. Its wavelength is much longer. Basically, it says the following. If you know E and M notation, K is 2 pi over lambda. That is called the wave number. And we are saying that K is much less than 1. Okay, that is what I'm trying to tell you here, but without mentioning this mathematical form. So now we have this idea. We want to now write down explicitly what is H of T within electric dipole mechanism. I already told you this picture. The atom nucleus, there's an electron density with some wave functions, Schrödinger wave functions. And then EM wave comes in, oscillating. Once it oscillates, the nucleus, which is the positive charge, and this cross, I try to depict the center of mass or center of gravity of this electron density. They deviate in location. So you have plus charge, minus charge separate by distance. This is called electric dipole moment. All right? And more, it is shaking. So you have a electric dipole moment that is varying in time. So you have a time, so-called oscillating electric dipole moment. Now, even if you think of this in terms of classical mechanics, there is a restoring force, right? Once this deviates from that, it will try to come back. So the atom has some characteristic frequency actually, and now an incident light try to shade it at some omega. You know what will happen? Some resonance will happen, right? Even classical. This is a mass spring oscillator with a forcing current. I think you have done it in classical mechanics. You know the response. There could be a resonance, and you will see that is exactly the same physics, but exhibiting it in quantum mechanics. The resonance means later on in quantum mechanics, I have this initial state, I have this final state, the incident light h bar omega must be of the right energy in order for this absorption or stimulated emission to occur. That is resonance, right? So this is what I just said. A remark is that even classical physics remains very helpful and useful. So let's go on to write down a Hamiltonian for this interaction. We are playing with electric dipole moment interacting with electric field. So therefore, look into Griffin's textbook, you find such a expression. Here, I follow standard quantum mechanics notation. In E&M, you may have this form, minus the electric dipole moment is usually written as P, but P is so important in quantum mechanics, it is momentum. So in quantum mechanics book, usually this electric dipole moment takes on something like the magnetic dipole moment notation, but make sure that you understand it goes with the electric field, it is electric dipole moment. Okay, so now we have the think classical part. Then what is the electric dipole moment in an atom? The simplest way is to think about a single electron situation. So I have a one electron situation. The nucleus is at 0, 0, 0 at the origin. The electron is at somewhere called position R. Then, again, in Griffin's book, the electric dipole moment is given by the charge of the electron times its position. Okay, so now we have everything. This is the electric dipole moment. I don't know whether you know this. If this is the charge density at a position R prime, okay? And then this is the electric dipole moment of a charge distribution described by the charge density. Oh, 你有冇學過呢？ Have you learned this? Have you done anything called multiple expansion in E&M? Okay, so when you have one charge, you know that, okay, good. Now, if you have one charge, the charge density is a delta function at the location of that charge. Then you will have equation 2, all right? Now, if you don't know this, don't worry. We are doing just single electron atom as an example. You just take this. Well, that has the right unit, first of all. What else can it be, okay? So we have everything. Let me summarize. This will be our interaction term. We'll have to turn something into an operator to go into quantum mechanics, but we know the form. And this is the form for this meal, okay? So the next page will be the punchline. So now we have EM waves. Let's look at how to write down the field. So I need this. In electromagnetism, the E field can be written as something like that. Okay. But if you use this complex notation, actually you're thinking about the real part. Or for our purpose here, I would like to think about it as real stuff. It is really real. This is just for convenience in classical electrodynamics. So the field will be a vector amplitude cosine KR minus omega t. If you want to include a phase here, the third term, fine, doesn't matter. So this will be our field. This is a vector. It is telling us what is the polarization. Where does the E field point, right? So for example, we will use the simple case of linearly polarized light more often. In that case, let's say the E field is polarized in Z. What does it mean? It always points at Z, but it will be longer, shorter, zero, negative Z, very long negative Z, and so on. But it is always along this Z. All right. So that is called linearly polarized light. This is arbitrary. We just set it to be the Z, so the propagation direction is in somewhere else, it's not in Z. So this is Z, and my field points at Z, okay? But this is just one case. You could have circularly polarized light, then your E field may be pointing at somewhere on this plan that is called XY. The propagation direction becomes usually taken as Z. That is all E and M classical. Now we make use of our argument. Our argument was the wavelength is much longer than the size of an atom. What we are saying is that when we look at this K dot R term, this is 2 pi over lambda, and you have this R, means the field here, when it goes through the atom, it will interact with the atom, but the atom's size is just A. So this term K dot R is typically of magnitude 2 pi over lambda times A. That goes like the size of the atom divided by the wavelength, which is much smaller than 1. Therefore, we will ignore this term or take it to 0, and then we simply pick up the time part to consider further the physics. But this is already very important because we will pick up the incident angular frequency. That is to say, at the end, we will have to find out the atom initial state, final state. There is a difference in energy. Incident light, there's an omega. What is the condition between this difference and omega that absorption could occur? So that piece of physics is retained. But the wavelength dependence is now ignored for the reason long wavelength compared to the size of the atom. Let me hint at more. If you keep this term, or at least first order to this term, you will have more complicated expression, and the result could be higher multipoles. So we are doing only electric dipole. So let's put linear polarized light for this case. Then we will have amplitude of the E field, linear polarized at Z, and then cosine omega t. So we have to play with time-dependent field. So finally, this is the most important page of this section. We have the precise form of the perturbation term, H prime, that has to do with matter, electric dipole moment, light interaction. Okay, so realize, let me repeat, it is an interaction term. It must consist of something related to matter, atom, the electron in the atom. It is here. It must has to do with something related to light. It is here. Okay, we remember, we do spin orbit interaction. That H prime must have something with spin, must have something with L, right? The orbital angular momentum. You see that S dot L term. It is something conceptually very similar here. Okay, so this is the starting form Now, more explicitly for single electron situation, this is minus E times the position of the electron. We have this situation. Then we can think about linearly polarized the situation, write this as an amplitude times Ez. Therefore, this is a form that we will work on rather extensively on the later pages. So finally, we have several forms for the interaction term. They are equivalent. One is more general than the other. Okay, so this is most general. This is single electron atom. This is linearly polarized light. Okay. So let me summarize what we have done. Now we have a situation. We have Hamiltonian of the atom alone. You know how to solve it. Then we have an H prime. The H prime is formally, now this is important as well, it is formally R and T, where R is the position of matter, the electron's location, you see? And then this T is attached to the light angular frequency, okay? So you do see a time-dependent perturbation term now. For our Schrödinger level treatment, we will not need to include the free or the light part of the Hamiltonian, because we are not going to quantize the EM field. This treatment, atom Hamiltonian plus this equation 7, H prime, is called semi-classical treatment of atom interacting with light. By semi-classical, we mean the following. For the atom and the interaction part, the interaction calculation, we use quantum mechanics. But in describing light, we are using classical EM theory, cosine omega t, okay? So we are setting up the stage. So let me define the problem, and then we will take a break, and then we will try to see how to solve equation 9 here. So now we have a take-home problem to do. The full Hamiltonian has been changed. We have atom Hamiltonian plus H prime. I emphasize the time dependence here. Actually, there's an R dependence as well. But that the new element is the time dependent. That's why we need to learn something new. Okay? So this is the problem we need to learn how to solve. But at this point, let me emphasize one more time. You see atom things here, you see light things here, and then this is the interaction term. Remember, the question is initial value problem. So we have to set a time. Before that, this term is not there, so we call that time 0 or negative time. Negative time, this alone. And the atom is in some 100% known to be in some initial state. Time equals 0. Afterwards, this kicks in, switch on. Then you ask, after it's switched on for some time t, what is the probability of finding the atom not to be in the initial state anymore, but in some final state? So that is the question. That is the corresponding technical problem to solve. Okay, so it has to do with a system starting from this state evolves in time. Okay? So this is the pictorial way to state the problem. When we ask question about transitions, although the full problem is these two terms together, but we are focusing on the atom part about transition. So although this is the full Hamiltonian, we are asking the atom part, initially here, final there, what is the probability? Okay, so take this in mind. Finally, if you are lost about what is the question, this is a baby level thinking. Hydrogen may be too complicated. Let's think about particle in an infinite well. To solve this, you know there are discrete states, energies. So this can be taken as our 1D atom. All right. Let's say it is in the ground state. You even know how to draw it. It is sine function, sine pi x over L, right? So now let's think about it. At time equals 0 onwards, you start shaking the bottom of the well. Okay, so this is smaller omega. This is faster omega. You understand me? Okay, so for a particular omega, you are asking, let's say initially is here, after 1 microsecond, what is the probability it is found here? Okay, so do you understand the questions? That is the question. Okay, easier to think about. And it is also easy to think about. It is a question that we need to consider, meaning transition could happen. So that is complicated, but of course you can even think about, now there is a particular difference, energy difference. If I divide it by h bar, there's a particular embedded frequency in the system. And if I shake the bottom close to that frequency, some resonance may occur, right? Reasonable. No fancy physics, it's not quantum at all, it's classical mechanics basically. So now, on this page, I try to convince you that there is some phenomena that we can study. So now, let's say I don't even need to shade it to understand there will be transitions, right? Even use some perturbation theory, the old one, you know there will be some transition. So let's say time equals 0 is flat, okay? And then at some time t, suddenly you turn on this. That is time dependent, but a very dull time dependent, time less than 0, time positive, okay? Nonetheless, it's tilted. Let's say the wave function adapt to the tilted well. You know that the ground state becomes something like this for the tilted well. To make use of this lower potential energy on this side, the wave function tilted to the left-hand side. So, but we are focusing on the atom. What is the atom? The atom is the flat bottom atom. Now with this state, for the tilted well, we know that this can be written as some coefficient times the ground state of the flat bottom atom, and then plus another coefficient times the first excited state. This side is positive, this side is positive, add it up to more positive on this side, right? This is positive, this is negative, diminishing the wave function on this side. So that makes sense. And now you already see, if I focus on the atom, which is the flat bottom system, even time equals 0 tilted, I already discovered that A2, if I take this square of it, it will be the probability of finding this atom to be in the first excited state. You see, time-dependent perturbation leads to transition. Okay? Now, you have all this big picture. We are ready to go into the mathematics. Okay? So let's take a break, and then we will try to derive from Schrödinger quantum mechanics how to get at this A2 or other states, not only the first excited state, this A2 at a time t after the perturbation start to comes in to interact with the atom. All right, so I hope at least you know what the question is and why we have this H prime being time dependent. That are the major take-home messages for this part. So let's take a break now. We will resume to do some time-dependent perturbation theory.